So we'll start today with the definition. This is just the definition of a vector in Rn. Now in chapter 4 we're going to generalize this idea to different kinds of objects, but for these first three chapters, chapters 1, 2, and 3, we're going to consider a vector as an ordered list of n numbers, typically written as a column. And n is some integer. This letter z stands for integers. And once again, this little symbol stands for in the setup. So this is a vector in Rn, where n is some integer, positive integer, and it's an ordered list of numbers. I think technically we should add a little superscript plus here. It has to be a positive integer. All right, so let's look at an example of a vector in R3. So here is two vectors in R3, 1, 2, 0, and 0, 2, 3. And we're going to graph these today. So typically we have x coming towards us, y going to the right, and z going up. So the way that I graph vectors is I draw a little box, and then I draw an arrow from the corner, the origin, to the other corner, the outside corner, the furthest corner from the origin of the box. Okay, so I go out 1, and then I go y is 2, and then I go z is 0, so I'm right here. This is my location. And now I'm going to draw my arrow from this location, from the origin to this location, like that. So that's my vector v. And now let's draw a vector u. So u is 0 in the x direction, 2 in the y direction, and 3 in the z direction. So it's right here. It's in the zy plane. And you can see it's kind of going from the origin to the corner of this box. All right, so those are my two vectors. Now often I will use x1 for the first entry, and this becomes our convention as the course progresses, x2 for the second, and x3 for the third. So sometimes I'll do z, sometimes I'll do x1, x2, and x3. Okay, now let's look at adding and scaling vectors. So let me just make this a general statement here. Vectors can be added and scaled. And when we scale them by real numbers. And I assume most of us have seen this happen. So let's look at u plus v, and let's consider 2v. So let's see what happens to these vectors when we scale them and add them. Okay, so we can do this both geometrically and algebraically. The way that we do this geometrically is we draw the first vector. In this case, it would be u. Let's do v first. This is commutative, so I can do v first. So here's my first vector, and then I'm going to take my second vector and start where the first vector ended, and then go from there to my endpoint. So u looks like this. And then u plus v is going to be the arrow from the start of the first vector. Let's do that again. Oops. So it's this arrow here. This is u plus v. And you can see this component-wise also. And if I had done u first and then v, I would go there and then I would go here. So you get the same vector, and that's what I mean when I say it's commutative. This sum, you can go u and then v, or v and then u. And the sum is that diagonal. You can also do this component-wise, so if you just add the components, the x1 components, the y or x2 components, the z or the x3 components, you'll see that u plus v is 1, 4, 3. And we could do this if we did 1 out, 4 this way, and then 3, we'd end up right there. And in this 3D situation, so let's go ahead and graph this. You draw a box. It's a little hard to see here, but 1, 4, and then 3 up. So it's 1 in the x direction, 4 in the y direction, and 1 up. And that's the terminal point right there. All right, now let's look at 2v. And scaling is very straightforward. You just stretch the vector by the scale factor. So if it was at 1, 2, now it's going to be at 2, 4. So my scaled vector is going to be this. This is my 2 times v. And you can see this by just taking the components and multiplying them by 2. Pretty straightforward.